Okay, thank you. Yeah.
Okay. Thanks a lot for giving me the invitation to talk. Hopefully everyone can hear me. All right. So yeah. What I wanted to talk about and tell you about today is some recent work that I did trying to understand infinite distance limits from the bottom up. And so that's the main goal. Hopefully, by the talk, I give you a better sense for what an infinite distance limit means from a low energy observer's point of view. And basically, this work was motivated by a particular observation. So let's say that we have a family of CFTs that are related to one another by exactly marginal deformations. So I take, schematically, I take my action and I can deform this action by some marginal operators. And this will span some conformal manifold. Now, this family naturally has a metric on it called the Zamolodchikov metric. That's related to the two-point function of these exactly marginal operators. And we know from some work that these authors did that there are infinite distance points in this metric where there's some dramatic behavior. They showed that, or argued that there should be some exponentially light higher spin fields that appear in that limit. So the motivation for this work was an observation that there's another metric that one can define on this family called a quantum information metric. And schematically, this is also be written in terms of the two-point function. And the benefit of this metric is that it can be defined for arbitrary families, arbitrary continuous families of theories. It doesn't matter what the deformation, I can always define this metric, and it quantifies something about that family. And the observation is that if I work at very large, if I put my theory in a box with some UV cutoff, and I work at large IR and UV cutoff, then this information metric inherits the parametric dependence on var phi, the parameters that parameterize this conformal manifold, and we get a proportionality between the information metric and the Zamolodchikov metric. And so importantly, the parametric dependence, the dependence on var phi, is shared between these two. So anything that's infinite distance in this metric is also infinite distance in that metric. And in fact, you can play the same game for like a nonlinear sigma model, where it's a theory that's specified by the metric on moduli space or the metric on field space. And we find there also that this information metric is proportional much in the same way as it is for the Zamolodchikov metric to the metric on moduli space.
So is this obvious that this is symmetric between A and B? Is it time reversal C? So it's not
so in this form, I made some assumptions about the nature of the operators. So it is indeed, this is assuming that these operators, that it's time reversal invariant, so that I can make permutations. Okay. But in general, there's another form that is obvious. You symmetrize over the indices. I also assume that the one-point functions vanished, just to be able to fit the equation on the slide, essentially.
And you're taking epsilon to 0, correct?
So I'm thinking of epsilon as this quantity is going to be a divergent quantity. So we need to regulate it in some way. So I'm thinking of it as very large, and then I'll study a version of it in which these divergent factors are canceled off. Much in the same way, you can talk about energy density versus energy. I look at the energy in a very large volume and divide that off by the volume. So the nice thing about this information metric is it's a general quantity. It can be defined arbitrary deformations of in a family of quantum field theories or theories, quantum theories. But when I restrict it to more symmetric classes of theories, it reduces to these more familiar metrics. And so the motivation, the swampy motivation for this work is trying to get a better understanding of, from the bottom up, what is the swampland distance conjecture telling us? We have a pretty good understanding by now, thanks to the work of a lot of people in the audience, that what's happening from the top down. We have a microscopic description or microscopic understanding in terms of fields becoming extra light. We're still, I think, missing a bottom-up understanding of this conjecture. And just more generally, I think the interesting question is, if we have a family of quantum theories, how do we encode the relationships among them geometrically? It's usually a very powerful way of studying different families of things. And it would be nice to have a better understanding of what the geometry of general theories are. So the metric is the ways of doing that, but it's not quite clear what it's encoding. And in order to understand what that metric is encoding better, we can focus on a particular points in that metric, infinite distance points, and try and understand what that characterization of a class of theories is. So the other two questions that I want to answer, or at least start to answer, is what does it mean if a theory is at infinite distance in this metric? And what ingredients are required to realize that? So Zoom has blocked my screen a little bit. So the main point of this talk, the main takeaway, is that the information metric is a general way of characterizing how distinguishable nearby theories are from one another. If I had access to possible measurements, like discern measurements I could do, how easy is it? How many measurements does it take for me to be absolutely certain, or certain within some degree of belief that this theory is actually the theory that I'm considering, as opposed to another theory? So this metric is measuring how distinguishable different theories are, and theories that are infinitely far apart are hyper-distinguishable. I'll give simple examples of this hyper-distinguishability, but really what this means is that there are some measurements that I can perform that have no statistical fluctuations. They immediately tell me, they immediately allow me to rule out a particular theory. So this information metric has seen quite a bit of popularity in the last decade in the condensed matter community as a way of detecting quantum phase transitions. You don't need to identify an order parameter. All you say is that this information metric is capturing qualitatively distinct phases of a theory, and a different theory should be highly distinguishable from another phase. So what we'll show is that if I consider this information metric at typical quantum critical points, when I think of a correlation length diverging or some field becoming gapless, I can't get infinite distance points in higher dimensional quantum field theories, any non-trivial dimensional quantum field theory. And this just comes from the typical scaling behavior that you have around a critical point. So this feeling that finite distance points are somehow, this feeling that infinite distance points are somehow qualitatively different than finite distance points can be summed up in terms of a scaling language. Quantum critical points display a typical scaling behavior where I operator dimensions to critical exponents. And if we make assumptions about that behavior, then we can never realize infinite distance points. In order to get an infinite distance point, we can argue that necessarily requires some violation of scaling behavior. So one of the ways you can get this violation is by having a tower of fields, as we might expect from the emergence proposal. And so we can use this language, this interpretation of the Zamolodchikov metric and the moduli space in terms of this information metric as a way of getting a better bottom-up understanding of what the swamp-line distance conjecture is telling you. These points are at infinite distance because they represent qualitatively different theories. And that's something that does not need any reference to a microscopic description of states becoming white or fields becoming white. So in this talk, I'll only work in quantum field theory, simple quantum field theory, and just try and get our feet wet to understand interpretational aspects as a way of eventually, hopefully, to a more refined understanding. So this is the first time I've given a talk on this, so please ask questions. Yeah, please ask questions.
Question, yeah.
Yeah.
So I like for example, I like that it's clear that, yeah, you have a global symmetry restoration, then it's going to be qualitatively different, and then the infinity stuff. Can you think of another example? I don't know, like, can you think then of a limit that doesn't have a global symmetry restoration and has something else that would also make it qualitatively different? And then
so,
I think it's
so
going
I
to
think
use
that,
this to argue that, well, we have some global symmetry at infinite distance.
yeah. So I think for the, exactly. Whenever I have a global symmetry being restored, there is an expectation that, I pay attention to charge conservation. And there's something about quantum gravity that says it's very easy to detect non-conservation. For things like decompactification limits, I'm not so sure. You can kind of see that it is at infinite distance from the point of view of there are a bunch of heavy winding modes whose masses are very sensitive to changes in the radius. But why that would, what sort of measurements that corresponds to is not something that I understand. It's something that I want to understand better. So I'll talk about that a little bit more.
Yeah, in the decompactification, you also have like the gauge coupling of the KK photon going to zero. But yeah, I'm sure. Yeah, how you would see that?
Yeah, I'm not sure. There's something I want to understand a lot better.
Actually, to follow that point up,
yeah.
In a decompactification limit, as Arena was pointing out, there's the states becoming heavier and heavier, the winding states, and they sort of leave the spectrum. Is that something that this notion of information theoretic metric would immediately detect, that some states have left the spectrum?
So I think that is something that is a bit different from this point of view, because this information metric is something that you can just define on a class of theories without having to talk about effective field theories or not. It's just characterizing different, the qualitative nature of the predictions that your theory, your ensemble of theories would be making. And so from that perspective, it's not so clear whether degrees of freedom have left the cutoff, have left the effective theory or gone above a certain cutoff or not. In some sense, you get this hyperdistinction from the tower of fields is because of these arbitrarily heavy states are very sensitive to.
So is there a general, has anybody made a conjecture or looked into the statement that there's an anti-distance conjecture? That infinite distance, there are always states which exponentially go up in mass? Sounds like that question is what you're discussing. Sounds like potentially a correct statement.
Yeah. So let me proceed if there aren't any other
Sorry, Jan.
Yeah.
Yeah, sorry. Can I have one question. Is it possible to get a, so you say if your tower of fields generates infinite distance, can you get infinite distance in this metric without tower of fields?
Yeah, so that's a good question. So the thing that I can say is that if I'm asking when a quantum critical point can be at infinite distance, that necessarily requires that this critical point is atypical. It doesn't display the type of behavior that most quantum critical points that we're familiar with do. Whether or not that there are quantum critical points in condensed matter, for example, that are able to realize an infinite distance singularity with a finite number of fields is a question that I'm also quite interested in understanding.
Yeah.
So I think, looking at the literature, there's been studies of these kind of atypical theories, but it's not quite clear whether those are infinite or not.
Thanks.
Yeah, no problem. Yeah, so the tower of fields is a sufficient thing, and one of the what would be very nice is to show that it's necessary in order to get such an infinite distance point. Okay, let me begin by talking a little bit about some classical information theory, just to kind of get a sense for what an information metric is and why I say it's related to the distinguishability of theory. So what we're going to do is we're going to study a statistical family, which is just a set of probability distributions that are parameterized by some continuous family. And I'll always use var5 with an A to denote these parameters. This family sweeps out something called a statistical manifold. It's just a space of probability distributions. And one of the maybe central questions in classical information theory is how do we characterize this family of distributions? So ideally what we'd like to do is define a measure of separation between two distributions. Almost like a distance, but not necessarily as constrained as a distance. And the most useful type of measure of separation that you can define between different probability distributions is something called a divergence. So a divergence has two properties. It's like a distance, but it's not necessarily symmetric, and it's two arguments. And it's always bounded from below. It's only zero if the two probability distributions are exactly equal to one another. And it's also defined so that its first variation is zero. Okay, so this will be necessary in order for its Hessian to be positive definite. Or said differently, we want to define a measure of separation between two distributions that's kind of convex. Convexity is a very useful property. So there are a lot of divergences like this, and sometimes it's more useful to study one versus the other. But the thing that is perhaps the most powerful is called the relative entropy. So this relative entropy is very useful. Its form follows from some relatively well-motivated axioms. It's kind of a unique thing if you assume that, it should be reparameterization independent and conditionally independent probabilities kind of factorize. But perhaps most importantly, the KL divergence has a nice operational interpretation, which can be phrased in terms of Sanov's theorem. So Sanov's theorem can be illustrated using just a coin, bias coin. What's the probability that we're fooled into thinking that a coin, the bias coin comes up heads F% of the time, or with probability f, and it tails with probability 1 minus f, if the actual true distribution of that coin has heads coming up with p probability. And so Sanov's theorem essentially says that as I perform more and more measurements, it becomes easier and easier to distinguish these two distributions. And the rate at which it becomes easier, the rate at which this Gaussian peaks around the true distribution, is given by the KL divergence. And so what the KL divergence does is it describes how distinguishable two distributions are in the limit that I start taking a lot of measurements. In that I take many samples. So there's a convention that we can say that two distributions are distinguishable in n samples or n measurements if n times the KL divergence is greater than 1, just so that we're on the downward slope of this Gaussian peak. Okay? So then what we can do is we can consider nearby distributions, infinitesimally separated distributions. And the properties of the divergence tell us that it starts at order, infinitesimal squared. And this thing can be interpreted as a metric. It's positive definite and has quite a nice set of properties. So this metric is called the classical information metric, or the Fisher information metric. And its interpretation is naturally tied to distinguishability. There's a natural notion of distance defined on the statistical manifold that is tied to how easy it is to distinguish different members of that family.
Sorry, John, can I ask a quick question? Can you see, is it easy to see that the metric is positive definite? That is Riemann metric?
So yeah, so it essentially follows from this. You say that it's, always greater than 0.
Thanks.
Yeah. So that was one of the crucial things in defining what a divergence is, and it's maybe not. It's a standard exercise to see that this is actually convex. It's one of the reasons why it's the log appears there. So then what we can do is we can play our Sanov's game, infinitesimally, and say that at each point, given a certain number of samples, at each point in my statistical manifold, I can draw a little ball or ellipsoid of distinguishability or indistinguishability around each point. And what this information metric is measuring is, say I give you n measurements and a curve along that statistical manifold. Then I just try and tile this curve with a number, of ellipsoids of indistinguishability. I count how many distinguishable distributions there are along that curve, and I define statistical distance as the number of distinguishable distributions, where I factor off a square root n over 2, kind of the RMS noise that I have. So the information metric gives me a notion of distance on a space of arbitrary probability distributions that quantifies how distinguishable different distributions are along that curve. So then we can return to our coin. KL divergence was singular, blows up if p equals 1. And that's a reflection of the fact that if I only get heads, if I say that I'm only going to get heads and I sing a single observation of tails, then I can immediately rule out that it was p equals 1. There are events that happen for the p equals 1. Sorry, there are events that happen when p is not equal to 1 or f is not equal to 1 that do not happen in the p case. And that singularity is inherited by the singularity in this information metric. The fact that that diverges is a reflection of the fact that there are events that do not appear, that it's easily distinguished from others.
Sorry, John, quick question. P equals 0 and 1 are at infinite distance in this metric then?
No, they're at finite distance in this metric.
They're finite, so could I say that this is like coordinate singularity?
Yeah, so that, because the statistical is defined in terms of counts, it's not quite meaningless to say that there's a singularity there. It's still a statement about, you know, this probability distribution being extremely distinguishable from the others.
Mm-hmm.
And the fact that the statistical length is dimensionless is kind of related to the fact that this is, you know, it is related to the fact that it's a count. And it's one of those, like, I'm not sure how it seems like a deep fact that enable to compare, you know, models with different number of parameters and stuff like that, because I can compare volumes to lengths and stuff like that.
Okay, thanks.
So,
can I ask a question about the previous slide? Yeah, this slide. In this biased coin, you give a nice interpretation of what it means to be at infinite distance, which is that you can make a single observation to know with certainty that you're not one of these things. On the last slide, you interpreted the distance as the number of theories, distinguishable distributions you can go through as you go along a path. Can you connect those two interpretations anyway? Like for the biased coin, can you explain why there's infinitely many different distinguishable distributions as you go towards?
So I would say it comes down to the square root n/2, this kind of RMS factor. You know, you know, in some sense, there's like standard distinguishability. Like as I take many, many samples, a central limit type, you know, behavior, and I start collapsing the Gaussian in a certain way. And I would say that the reason why you're getting this very large increase in distinguishability is you're kind of in this different regime of, sometimes it's a reflection of that. So this is, admittedly, this is something that I don't have a very clear, like, you know, intuitive understanding of how one divides different, like, how one separates in this distinguishability criteria, finite distance singularities from infinite distance singularities. But there's a sense in which they're easier to distinguish than, one's easier to distinguish than the other. So this was at finite distance. We can consider a simple example, which is at infinite distance, the Gaussian. If I imagine changing its variance and mean, it gives rise to a metric which is Euclidean ADS 2. And it has an infinite distance singularity when the variance collapses to 0 or the variance goes to infinity. And we can understand the appearance of this infinite distance singularity, this metric singularity, as a reflection of the fact that if I take the variance to go to 0, I could easily distinguish that distribution using any measurement, except, you know, I just measure the probability distribution, or I sample and see if there's any sample that is not at 0, at x equals 0, right?
Can I ask a question?
Yeah.
Oh, can you just give some intuition for why this should be an infinite distance singularity, whereas the coin flip was a finite distance? Because they seem very similar.
Yeah, so I think in some sense, so I don't have a rigorous understanding of it. In some sense, the alphabet that you're pulling these samples from is much larger in one case versus the other. So differently, there are many, many more ways that this can be non-zero than the coin can be non-zero. And that's kind of the flavor that I have for these infinite distance singularities is that they're much more distinguishable, and so I don't have to worry about like getting, you know, an incredibly biased point, but not p equals 1, and flipping a lot. I can get, you know, a simple Gaussian, and the set of measurements that agree with sigma equals 0 is measure 0 with respect to the other thing. So it's, you know, it's a different degree of distinguishability, but that's something that I'm still trying to understand. Are there any other questions?
Yeah, can I follow up on what Naomi just asked? So,
Yeah.
John, do you think that if I have, is it reasonable to say that if I have a distribution for a continuous variable, and at some point there's a finite volume region where the probability really drops down to 0, that would be the infinite distance?
That's my, I'm not sure whether it's measure 0 or finite volume. I would say that it's that case. This is certainly corresponds to a metric singularity, because the KL divergence is blowing up there. But I'm not sure if it's measure 0, if it's really a matter of measure or a matter of continuum. Maybe I should say it like that.
Thanks.
And one question I have is that I don't know if you have chosen this example judiciously, that you get the negative curvature at the infinite distance, which is typical in moduli spaces, or just randomly this happened to be. Is there any curvature?
I don't understand what the importance of curvature is for these statistical models.
I see.
I don't know if the statisticians have an understanding of what that means.
But they haven't even studied it, you mean? Whether the curvatures they get are typically negative or not?
Yeah, I don't know.
Yeah, okay.
It's something that I haven't looked into.
Okay.
Yeah, I chose this example because it's, beyond the coin, it's the simplest probability distribution that I could think of. It exhibits this hyper distinguishability. Okay, so that was the classical information metric. I said that the quantum information metric is proportional to these metrics that we're more familiar with, and so that requires introducing this quantum information metric. So the quantum information metric is defined on an arbitrary continuous family of states in a Hilbert space. And it's literally the Fubini-Studi metric on the ambient CPN, and I pull that back to the submanifold of states. And the reason why it's called an information metric is because if I take, if I write my state in this, I have the probability distribution associated with the state, and then this phase factor associated with the state, then I find that the information metric, the quantum information, is classical information metric plus terms that depend on this phase. That's kind of what we would expect. Quantum information theory is classical information theory plus phases in some sense.
So this is related to Berry's connection, of course, right?
Yeah. So when there's a Berry curvature in the theory, I can't remove these alpha terms consistently over the entire family, and I have to worry about it. But in fact, this quantum information metric naturally comes in a pair with the Berry curvature. So I can think of the quantum information metric as the real part of a tensor, whose imaginary part is the Berry curvature. And together they form this oddly titled thing called the quantum geometric tensor. So maybe said slightly differently, in cases where I have a complexification of these parameters, then the quantum information metric is just the from a certain Kähler potential, and then the Berry curvature is the form associated to it. So I want to try and understand just the interpretation aspect and all of the theories that I'll study, I can always gauge transform this phase away. And so the quantum information metric in that family, I don't have to worry about phases, and I just find that it's equal or proportional to the classical information metric. And this classical information metric, or this quantum information metric, can be derived from a divergence, which is just the log of the fidelity between the two states. This acts like a Kähler potential. Okay. So before I describe classical information metric, characterizes the distinguishability of a family of probability distributions. I just described how the quantum information metric, in this case that I can take away the phases, is the classical information metric. And what this does is it quantifies the distinguishability between different states. How easy is it to distinguish one state from another by performing measurements on it? And what we can do is we can say, okay, well, let me place a metric on this space of theories. Consider mapping each theory to its ground state and placing the information metric on that set of ground states. And so I'm able to provide a metric which characterizes the distinguishability of different theories if I'm able to perform measurements on their ground states. And it's this object, which is proportional to the Zamolodchikov metric and the metric on moduli space. So you kind of see that if I perform a deformation of like a Euclidean action by some operators, they say that this family is spanned by doing deformations with respect to some basis of operators. Then taking two derivatives of this will give me some sort of two-point function that I have to integrate over semi-infinite time. So this is kind of representing the fact that I'm computing the ground state of one, but with a small fluctuation in the operator that I'm perturbing the theory by, and then I need to sandwich it with another state. Okay. So now that we have this definition of what the quantum information metric is, it'll be helpful to understand how it behaves in quantum field theories. And perhaps the simplest way of doing this is to study how it behaves around critical points, or assume that this correlator at large distances takes this form, where there's some exponential suppression whose length scale depends on the correlation length, and then some natural like power law suppression dimension, and ask how does this metric behave when I assume this scaling. I find that depending on the scaling dimension, I can have either no dependence in the correlation function, a singularity, a logarithmic singularity as I take the correlation length to infinity, or a power law singularity to take the correlation length. And it's always dressed with this factor of L times lambda UV to the T. So the condensed matter folk have shown that at least in local theories, anytime I have a singularity in this metric that implies a gapless mode, the converse is not true. If I have a gapless mode, it doesn't necessarily imply a singularity in this metric. And what we can do is we can understand this factor of L times lambda UV to the D is kind of like the number of degrees of freedom that I'm keeping in my theory. This thing is divergent in the IR and the UV cutoff, because whenever I'm drawing from this ground state distribution, this ground state probability distribution, it's providing me with L times lambda UV to the D variables. And this metric is characterizing the average behavior of all of those local degrees of freedom, the average distinguishability of all those local degrees of freedom. So much in the same way it makes sense to define a potential energy density, instead of working with the energy, it makes sense to pay attention to the intensive metric, where I strip off this kind of very natural scaling with the cutoff and both cutoffs. And that's what we saw, that's what our motivation was that this quantum information metric was proportional to the Zamolodchikov metric, but with this now understood factor of the cutoffs. This intensive quantum information metric is proportional to the Zamolodchikov metric.
Yeah, one question. So I'm a bit confused about something. Like here, you got two possible types of divergence for the metric, the log of the polynomial one. Both can give rise to infinite distance, right?
Yeah, so that depends on, yeah, so that depends on how the correlation length depends on the parameters of the theory, which is what I'll talk about now.
Okay, so it's not clear yet. Yeah, I was wondering, like,
Yeah.
because with the distance conjecture, we always get only like one type, but to understand which one, you also need to know how the tower behaves in these coordinates, because otherwise you can just reparameterize the
exactly.
So, okay.
Yeah. So yeah, exactly. As Irena was asking, one, there's a very natural and good question to ask, which is, do I ever get an infinite distance singularity out of this quantum critical scale, this quantum critical behavior? And what that depends on is how the correlation length depends on the parameters in your theory, right? How the correlation length diverges as I approach this critical point. And that's governed by this critical exponent nu, the correlation length critical exponent. So just by looking at, the scaling of the metric with the correlation length, we can say that in order to get an infinite distance point in this parameter var phi, I need both this inequality to be satisfied, so that this is the overall scaling goes like var phi squared to the 2, or 1 over var phi squared to the 2. And then I need a metric. I need an actual metric singularity to get that infinite distance point. But if this critical point, remember that I'm perturbing by operators with a particular scaling dimension. And those operators were associated with my var phi parameters, in this way. Using the properties of that quantum critical point, we can relate the scaling, this correlation length exponent to the scaling dimension of the operators that I'm perturbing by. And we find that the point, this var phi naught, is at infinite distance when this inequality is satisfied. But since this is positive and this is positive in order to get infinite distance points, then the only time I can get an infinite distance point when the correlation length is diverging is if I'm in 0 dimensions. Okay. So I can rephrase the uniqueness of infinite distance points away from towers of fields and for just the nature of this critical point. It's a critical point which is non-standard. Okay. Are there any questions about that?
Yeah, John, I have a question. Like I'm looking at the condition you wrote down, and it seems that delta drops out of it.
Here?
Yeah. Like if I try to solve for deltas that satisfy that, don't they? Like delta drops out of both sides. I put the denominator on the right. and then I get d plus 2 minus 2 delta bigger than or equal to d plus 2 minus 2 delta, and the two deltas drop out.
Yeah, I think that's a reflection of the fact that this can never be satisfied for any delta if this condition is positive.
Okay.
And d is, I remember being confused by this, and I think that was.
It's like you need to have d smaller or equal than 0, and that's it. So it has to be 0. That's the only solution.
Well, yeah. So it has to. It's either 0 or this.
Okay, yeah.
This relation is violent.
Mm-hmm.
And we'll see. It's like exactly that in the power fields. This relationship is violated. There's an additional scaling that you would not infer just from naive dimensional analysis.
So when you say typical exhibit, like typical points exhibit this scaling behavior, is that, do we know exceptions to this within condensed matter?
There are exceptions that I found, but I don't understand what they are. It's on my to-do list.
Mm-hmm.
But typical, it follows from what? From nothing cannot be unitarity or things, because otherwise it'd be exactly true. So typical things, what's their motivation? Why do they get this?
So the question reduces to, why is the correlation length related to the scaling dimension of the operator in this way?
Right.
And that
John, is that
follows.
Could it be related, like that's kind of like the condition that delta is a relevant deformation? And it makes sense, right? Because when I have a CFT and I perturb away from the conformal point, from the point of view of the CFT, from the point of view of the quantum theory, I get a finite correlation length. From the point of view of the CFT, I'm perturbing by a relevant deformation. So that sounds right.
I think it's just like a you dilate things, and then you ask, how does the
I'm just saying that d plus 1 minus delta is positive. I think it's the same as saying you have a relevant deformation. That delta is the dimension of a relevant deformation.
So that's certainly true, but there's also a way of seeing this correlation, this critical exponent is related to the scaling dimension of the thing that you're perturbing by. I remember being puzzled by this. And
so is this space time or space dimensions here?
Sorry, D is spatial dimension.
Just so it's d plus 1 is space time. I see. Okay.
Yeah. Sorry, I should have mentioned that. Yeah. So if I remember correctly, it's like a 3-line thing, which basically follows from assuming like locality of the Hamiltonian, and certain things scale with others.
So this is a naive scaling, in other words.
Yeah, exactly. Yeah. So yeah, exactly. If I want an infinite distance point at a quantum critical point, then I necessarily have to have a violation of this naive scaling.
Yeah, thanks.
Okay. So as Irena points out, you need d equals 0. We already ran into the simplest infinite distance points in the harmonic oscillator. And again, we can understand this as, if I take the variance to 0, or I take the frequency to 0 or infinity, then either in momentum space or position space, there are measurements that I can do that immediately distinguish that limit. So now we can start descending up in dimension and asking, what happens for a free scalar if I'm changing the mass of scalar? And I find that in the massless limit, there are metric singularities, at least in lower dimensions. But these are never at infinite distance, as our scaling analysis would suggest. In contrast, there is an infinite distance singularity as I take the mass to infinity. So what we can do is we can understand both of these limits, why the infinite mass limit is at infinite distance, and why the mass is not at infinite distance, but paying attention to what's happening to the wave function. As I take the mass to infinity, I'm collapsing the wave function to 0 values, the field variable. So if I have this quantum field and I perform a measurement anywhere in space, and I detect the non-zero field value, then immediately I know I've immediately distinguished this theory. I've immediately ruled it out. But when I do this, the massless, confused by the spatial dependence, the k dependence of these modes washes out the distinguishability of this massless limit and turns it from an infinite distance limit, as it was in the harmonic oscillator, to a finite distance singularity. Okay? So the fact that there are a lot of different modes that are now insensitive to fluctuations of the mass near the massless limit means that this infinite distance singularity in lower dimensions gets downgraded to a finite distance singularity. So the spatial dependence of the quantum field theory washes out this hyperdistinguishability. And so the natural question is, how do we restore it? And this emergence proposal kind of gives us a natural thing to try, which is to consider a tower of fields. So if we study this quantum information metric in this tower of fields where I'm now playing with the mass spacing, I'm allowing the masses to compress at a certain point in this parameter, then I find that the metric takes a fairly universal form. As I said before, in the case where we just had a quantum field theory, we encountered a factor of the number of degrees of freedom. But because now I have more degrees of freedom, I'm considering an infinite number of quantum fields. Essentially, I get another infinite factor that I have to regularize by. But the intensive metric, the thing where I strip off the number of degrees of freedom, has this infinite distance singularity. And this form of this metric is universal for free or weakly coupled scalars and fermions. It doesn't really depend on the dimension of the lattice or anything. It just depends on the fact that I have an infinite number of things compressing in mass.
Yeah, one question here. How are you performing or regularizing the infinite sum? Like you.
So yeah, so there's a couple of ways of doing it. Essentially, all ways give the same feeling. So the first, maybe the most intuitive way, is to do just a strict cutoff on this sum over fields, and that gives you this L max. But then you can do a sort of like dimensional regularization where you get these infinite gamma factors.
And the strict cutoff will depend on mu, like on the mass, as happens when we perform the sum using the species bound, or is independent of mu?
So it is. So the L, yeah. So it's independent of mu here.
It depends.
It's independent.
Independent. Okay.
Yeah.
So just want to make sure, if you have suppose L is 1, suppose you just have one such state, your distance is not at infinite, is it?
It's not at infinite. Yeah, it's not at infinite distance. What's happening is what's happening is the ensemble of fields that are compressing in mass is what's responsible for this infinite distance limit. You can look into what's happening, and you see that the high modes boost in sensitivity to the changes in mu. Essentially, if I look at the variance of these modes as I change mu, the high L's get boosted by a factor, the change in the variance gets boosted by a factor of L squared, because these modes are very sensitive to changes in mu. And those high L modes are restoring the distinguishability of that limit. So it's about the high charge stuff rather than the low charge stuff. And so I showed this in free theory. I studied this in free theory, but because there's an infinite distance, because there's a singularity, you this whole for relatively, for moderate coupling, there might be strong coupling effects that can dramatically change the story. Have a tower of fields that doesn't give an infinite distance limit, or have things that do get an infinite distance limit but aren't a tower of fields. But at this point, I can't say what else can do that. And so, given this tower, we can actually.
Sorry to interrupt again. It's already 11:30, so if you can go quicker or wrapping up, would be nice.
Yeah, I will. Sorry. I mean, what you can do is you can see, you look at the type of perturbation that changing the mass spacing does to the theory, and try and understand how the scaling analysis that we performed earlier was violated. Why do we get a distance point? And the fact that you have this tower allows the operator dimensions, the effective operator dimension of this tower, to be different than what a scaling analysis would apply. You find that instead of this scaling like a mass perturbation, it actually scales with some weird, d plus 3/2, and all of the dimensions of the operator, all of the dimensions that are soaked up by the mass spacing. Okay, so to make Irena happy, let me conclude. So motivated by this observation that the information metric is related to the logic of metric and the metric on marginalized space. Can we use this interpretation of those two metrics as a way of better understanding infinite distance limits from a bottom-up perspective, without reference to some microscopic description? We're able to argue that this information metric has infinite distance singularities when the predictions that the theory makes are becoming qualitatively different, in the sense that there are some, it's very easy to distinguish that theory from others. And what this does is it formalizes this kind of intuition that the distance are qualitatively distinct. In some sense, it formalizes this intuition that the effective field theory should always break down because I have this qualitatively different behavior. And so, I have some words about what we need to, in order to provide a real bottom-up motivation for the swampland distance conjecture. Basically, identifying a set of height measurements and then using that as a way of arguing for a tower of things becoming white. But this is still from being realized. One very relevant question is, none of this analysis needed in Planck. So it's not clear how the Planck mass or the Planck scale comes in. What goes wrong if this type of behavior is there? So with that, let me end. Thank you.
Okay, thank you very much, John, for the very nice talk. So are there more questions?